So thank you for coming out. There's an iceberg, and thanks to Ed and to Dave Drew, and thanks to you for coming out. And there's a penguin, for what it's worth. And thanks also to the National Academy. I will come back to them because they do play a role in this. So we'll see what we can do. I want to start you off with the broad picture I'm going to walk through. I'm going to show you how much good we get from our use of energy. I'm going to show you why what we're doing cannot continue, and I'm going to show you a few of the options of why we can actually get to a much better place. So that's the broad picture. And I want to start you with the good we get from our energy system. And I'm going to do that via a trip that I took as we were writing this class on geology of the national parks. So a number of years ago, we got a dozen advanced students. We got the local PBS affiliate to teach them how to do filming, and we took them to the Grand Canyon and other places. We got them to the bottom of the Grand Canyon. We were hiking along by moonlight, and yeah, it was just a fascinating thing. And Stephanie here is explaining why the river is now clean when it used to be dirty, because there's a dam upstream, and there's the dam, and all the mud is on the wrong side of that at this point. And so we did, and this is geology of the national parks. So we mostly did geology, but of course we're driving by Mesa Verde. And you gotta go to Mesa Verde. And the truth is they probably got more out of that than any of the geologic ones. If you've not, anybody been to Mesa Verde? Right, fantastic place. I strongly advise it if you haven't been there. Now, I'm gonna tell you a story about people. Later I'll tell you about CO2 being a greenhouse gas. CO2 is a greenhouse gas. When I tell you a story about people, be very clear. I'm rounding off some corners. There's no way that I can give you all the nuance of what they did and why. But I'm going to tell you what the ranger showed us, and I believe I'm showing you a lot of what is correct. So we'll walk through that and see what we can do. If you haven't been there, right, it's this mesa down in southwestern Colorado, and people grew corn up on top, and they lived down on the sides in these glorious stone constructions. And so here, there's a ladder down here, and we're going to focus on the end of that blue arrow for a minute. You can see it in all the different screens. And this is, there it is again, a person for scale down at the purple arrow, and there's that blue arrow. That fairly clearly was a granary. That is where they kept their food. And what you will notice is that that is a remarkably difficult place to get to. And there's a lot of discussion, why would you put your food there? But sort of the leading idea, if there's anyone in this room who has ever had a package of Oreos and said, I really shouldn't eat the whole package of Oreos, maybe if I put it on top of the cabinet, right? Except this isn't the Oreos, it isn't the dessert, it's the dinner. And they're putting the food where it would be hard to overeat, hard to take what isn't your share, where it would be easy to control up there on the cliff. Okay? Now behind that structure, if you were to go way down in there, behind it, you'd see this. These caves are there for geologic reasons. The water seeps out along little shale partings. And so you can see there's a little water coming out on the edge of the cave. And right down at the end of the blue arrow again, you see this. Somebody has sat there and chipped holes in the rock, and there's a little bit of water in those holes. Now that, we had Cokes for dinner. This is not exactly at the same level, but if that's all the water in the world, it looks pretty good. Right? And these things, they built these walls with windows. And then later they took the effort of blocking them off. And if you fill up a window, you're blocking something out. But what's on the other side of the window are their neighbors. And up on top, if you're walking along across the mesa and you're ready to go down to see them, you walk by this. And the ranger said they built this, 900 years ago. And it's a little check dam, and it holds a little bit of soil, and that soil was a cornfield. And you want to hold the soil and you want to hold the water, and if that's a place you could grow a little extra corn, that helps. And then after living there for centuries, they left. Right? So it's very clear from looking at this that even at the best of times, this was a hard way to go. And at the worst of times, it was probably really hard. And then after that being home for a very, very long time, they left. Okay? Now, we can do something else with this. There is very little wood in this, but there is a little bit of wood, and you can see one right along there. And if there is wood, there are tree rings. And if there's tree rings, you can do tree ring science. In this dry environment, a tree grows well when it rains. And it doesn't grow well when it doesn't rain. And you can match from living wood to dead wood and archaeological sites, matching the pattern of thick and thin rings, and you can make a longer record than the life of a tree. So you can go in, and I didn't do this, but colleagues did. You can go in and get a record of how much it's rained here for long times. So you wouldn't do this study at Mesa Verde because Mesa Verde has trade. It's a big place. There's a lot going on. But if you sort of look down from Mesa Verde, you can just about see Longhouse Valley way on down into Arizona. And so teams of scientists went down to Longhouse Valley. And one team was tree ring people, but they're working with anthropologists because if rain grows trees, it can grow corn. And if you talk to Puebloan people and figure out how they lived and how much corn it takes and so on and how long a generation is, trees give you rain, gives you corn, gives you people, and you can ask how many people could live here. Then independently, they got a bunch of archaeologists who went in and did the classical thing. Who's buried here? Whose ruins are here? How many people did live here? So now you have two independent lines. How many people could live here? How many people did live here? And so here it is. And you've got the year 800 on your left, the year 1300 on your right. There are some knobs in the modeling, and we could argue about this a little, but from where you're sitting, the two curves within the uncertainties are basically the same curve. How many people could live here? How many people did live here? When the rains came, the population came. And when the rains went away, whether they quit having babies or whether some left or whether the babies died, we don't know, but those are the only three options. And the rains came back, and then when it crashed at the end, when it got pretty low, they said, screw it, we're out of here, and they became environmental refugees, and they headed down along the Rio Grande. And so to pretty close approximation, they were at the carrying capacity right on through. They're listening to the climate very, very closely. Now, let's do one more drought, and then we'll come back on this. You probably read about this one at some point. Oklahoma in the 1930s in the Dust Bowl, people leaving to head to California. But see what's in the back here. They've got gasoline to drive away, but they've got power that could run a pump. They've got, and a truck can bring food as well as take somebody away. And you see, this is a different looking world now. And here is the same plot in different colors. So 1900 is on your left, 2000 is on your right. The red here is the Palmer Drought Severity Index, but that's basically, you can think of it sort of as rain. And the Dust Bowl is right here. And then there's some other droughts. This is population. Despite everybody leaving, despite all the Okies headed to California, basically the population just stabilized. The dip here is actually World War II. The people of Oklahoma didn't starve to death, and they didn't all become environmental refugees in the Dust Bowl. And the difference is mostly because they had pumps, they had power, they had trains and trucks to bring food. They were established in a trade network with the ability to do things. Now, be very clear. There's a lot of smart people in Oklahoma figured out how to do this to keep themselves alive and going during that. There were a lot of smart people at Mesa Verde. If you took us and dropped us on that mesa top with what they had and asked us to get through a winter, don't kid anybody. There's no chance that we would get through with it. They were really smart people. Really smart people failed at Mesa Verde eventually when the drought hit, and they succeeded in Oklahoma. And the difference is mostly what we've built, what we've gotten from our ancestors, our knowledge and our ability to power it. It's not this, it's how this is turned into things that we can use. And so you get to this, we were chatting up here earlier, I give a different talk sometimes on the fact that the earth was probably overpopulated with a few million hunter-gatherers. And we are now a few billion read, write, grow, build, teach learners. And, it's just truly amazing. Right? Go into a 5th grade class sometime and ask them what this is. They'll say it's a cell phone or a phone or a smartphone. Then if they're sharp, they'll say, wait a minute, that's a little one. You're sort of not with it, are you? And then you say, what's it made of? And if there's somebody really smart, after a minute, they'll say, cell phone parts? What's it made of? It's a little bit of oil for the plastic. It's a little bit of sand for the glass and the silicon and the chip, and it's the right rocks to get the right things out of. This is sand, oil, and rocks. And I will guarantee you, if you took the sand, oil, and rocks and took them to the Senate and said, turn this into a cell phone, you would wait a long time. Right? Einstein's in there. Feynman is in there. This is science and engineering writ large. It works. And yet I guarantee you that we know people who will use this and send me a note that says, you scientists don't know what you're talking about. It's very interesting. Okay, so at any rate, so science and engineering work, and they are really important for us. I'm going to walk through a piece of sustainability. Sustainability is food, it is water, it is a bunch of things. We can make an argument that energy is probably more important than the others, except getting along with each other. And so I'm going to do the energy story for you. And so we'll hit this, right? So when they calculate the recommended daily allowance of whatever it is, they usually figure on 2,000 calories. Okay, I had the ice cream after dinner. I'm not sure I kept mine to 2, but we'll use that. Okay? What I can do for myself in a day is 2,000 calories. But the ice cream was cold, and the pizza was warm, and they both had been brought here from somewhere else, and the room is lighted, and the room is heated, and I drove down here from State College. If you take the total energy use in the U.S. and divide it by the number of people and convert it to these units, it is 240,000 calories a day. What I can do for myself is 2,000. What is done for me is 240,000. It is if I have more than 100 serfs to do my bidding. Serf cook for me, serf heat me, serf cool me, serf pick up my car and run down the highway at 70 miles an hour. Right? And I love this. Okay, this is great. And we all love this. It's about 85% fossil fuels. So right now we get an immense amount of good from the energy we get from burning fossil fuels. And there's just no way out of that, okay? I'm going to walk you through a couple of little historical vignettes. We have a long history of getting energy by burning something fantastically faster than nature makes more of it, dealing with the consequences of burning it, dealing with the consequences of running out of it, and then looking desperately for something to replace it. And while we have become farmers of food, we remain hunter-gatherers of energy. And so let me walk you through this. I come to you from central Pennsylvania, from State College. State College is a suburb of Penn State. When Penn State was founded, there was no town of State College. What there was the iron furnace. And this is our iron furnace, the center furnace. And there would have been 100 people taking care of the center furnace. And the iron masters founded Penn State up the hill from the furnace, and then the town grew up after that. But it truly is that State College is a suburb of Penn State, and Penn State is here because this is here. When the furnace was running, it would have looked more like this. It was turning red dirt, limestone flux, and charcoal into pig iron. And the east was built of Juniata iron. And the charcoal was from trees. And to keep a furnace in blast for a year was a bit over a half a square mile of trees for a furnace. 100 people, and they're heating and cooking and building houses, and a half a square mile of trees for the furnace. You're talking a square mile of trees per furnace per year. Okay? They made charcoal like this. This is done late in charcoal making. These are fairly small trees. They would make one of these giant piles of logs. They would bury it in dirt. They would, before it's buried, you can sit on top of it. Once it's buried, they burn it. Not much oxygen. If the dirt cracks, somebody has to get up on top and fix it and hope you don't fall through. And what did it do? It did this. Okay, a square mile of trees for a furnace for a year. If you go today to a gazetteer of Pennsylvania and you ask the map, where does the name furnace still exist in Pennsylvania? These are the furnaces. Okay. Each one of these, plus a whole lot more that are no longer place names, a square mile of trees a year when it's burning. These are the forges where the pig iron is turned into Valley Forge and others. The pig iron is turned into valuable things, another square mile of trees. The trees were gone really fast. Right? The first forester of the Commonwealth, Rothrock, at one point was a professor up with us and then over in Philadelphia. This is Penn's Woods, right? We are Pennsylvania, Penn's Woods. Rothrock wrote about the Great Pennsylvania Desert. Now, it wasn't a desert. It still rained, but there were essentially no trees. There's 1 million deer in Pennsylvania now. They were basically gone. We have elk because we re-imported them from the Rocky Mountains. We chased the elk out. We chased the bison out. We're the Nittany lions. There's no Nittany lions. There wasn't a tree to do it behind. Okay, basically everything bigger than a rabbit or a squirrel we traced out, as well as burning all the trees. And it wasn't just us. The whole east is stripped of trees almost completely. There's very little that's left that was from original. Okay? Now, if you've ever tried to read by firelight, it's not very easy. And if you're going to do 12 stitches to the inch on a quilt, it's really not easy. So what do you do for lamp? You know, you could burn candles, animal fat or something. That's not very satisfactory. They used to use a biofuel they called camphene. It was a mixture of alcohol and turpentine. It was renewable. It was fairly cheap. It burned cleanly, but it tended to blow up if you weren't careful. And you can find just horrible stories. You know, the Methodist minister and his wife go out to visit the parishioners, and the 3 daughters try to refill the lamp, and they burn themselves to death. And the rich people burned whales in their lamps. And so you would send Yankee whalers out to scour the world ocean for whales, and you'd cook them and you'd bring it home, and it burned cleanly and it didn't stink and it didn't blow up. And so this is the history of the whale oil production from the Yankee fleet, 1800, 1880. This is a complicated story. There's a civil war in here. There's the fleet being crushed in the sea ice off of Alaska and the insurance rates going through the roof. But what's the fleet doing in the sea ice off of Alaska? They couldn't find whales they could catch closer to home. And there were some whales that were too fast for them that the Norwegians took out later. But basically, here's whaling. Okay? By the time you get there, there's virtually nothing left in the world ocean you can catch with this technology. They're gone. And a few remain, so they grew back when we quit killing them, but as a practical resource, they were gone. At this point, there are 10,000 sailors out of New England scouring the world ocean for whales. And you see what happens after you go over the peak. This right here is about $7 a gallon for lamp oil in modern money. And when the peak hit, it goes up to about 23. And then they go up the road from us up here and they drill the first modern oil well. Okay. Now, that's quite a history. We can't go back, right? 10,000 whalers mining the ocean for whales at a rate far faster than they grew back. You know, sort of a week of U.S. oil imports recently. 100 years of whaling with 10,000 at the peak for something like a week of imports. Right? The idea that we go back is completely absurd. But we have whales and we have trees because we switched to burning fossil trees and fossil algae. And they knew this all the way back then. So this is an editorial cartoon published in the magazine Vanity Fair in the year 1861, and you can read it. It's the grand ball given by the whales in honor of the oil wells of Pennsylvania. And this is right before the Civil War, right? So the oil wells of our native land, may they never secede. Oil's well that ends well. Okay? We have whales and trees because we burn fossil trees and fossil algae. And we can't keep doing that. And any economist worth his or her salt hates this term. They'd say, no, resources never run out. They become uneconomic relative to alternates. But the fossil fuels accumulated over a few 100 million years. We are burning them over a few 100 years. We are burning them 1 million times faster than nature saved them for us. The rate at which new ones are being made is essentially zero. There is nothing, there is a bank account out there and nothing is being added to it. Why did they drill the first oil well where they did? Well, oil was flowing out of the ground. And they said, wow, if oil comes out of the ground, maybe there's oil in the ground, we should drill here. Okay. What is BP doing in the Gulf in deep water, spending millions trying to get a new one? The easy stuff is gone. Right? Few of you are old enough and gray enough to remember when there was a situation comedy about our energy system on television. Right? It was a story about a man named Jed, who was a poor mountaineer and he barely kept his family fed, and one day he was shooting at some food and up through the ground come a bubbling crude. Oil, that is, right? And you could do that because there was a time that oil was right there at the surface. The easy stuff's gone. Right? Now, admittedly, if we frack it all, if we take off all the mountaintops, there's a lot more left than what we've burned, but the easy stuff really is gone. And just how much of it we've used, right? We were talking earlier today. What we throw away at the curb for the trash collector is a little under 1,000 pounds of stuff per person per year. What we put in the atmosphere as our share of the CO2 from the U.S. economy is almost 40,000 pounds per person per year. The CO2 so grossly dwarfs our normal trash stream. If we could see it, we would not be having this discussion. And just how fantastically good the fossil fuel companies are at getting us what we ask for, that they're supplying us enough to make 20 tons of CO2 per person per year is pretty amazing. Okay. But in addition to the fact that this cannot be a long-term solution, it has some other problems. And so the physics, we put CO2 in the air, this affects radiation, has been known well over a century. It was worked out especially well up at Hanscom Air Force Base in New England right after World War II for a number of reasons that were not global warming. And one of those was sensors on heat-seeking missiles. One of the jobs of the Air Force after World War II was making sure that bad guys with bombs didn't do really nasty things to big cities. One of the ways you can do that is that the enemy bomber will have a hot exhaust. You can follow the hot exhaust. You can fly up the tailpipe and make sure he doesn't get to your city. But if you put the wrong sensor on your heat-seeking missile, you cannot see the infrared radiation from the hot exhaust of the enemy bomber, because CO2 soaks it up and transfers it to the other molecules in the air, and it doesn't get to you. And so they paid some good physicists to figure this out. Now, I can tell you, even today, even on a rainy, gray day, the sun heated the Earth sent radiation back to space, and there was more radiation going up from the sun-warmed Earth than coming down from enemy bombers. This is a satellite image. It actually shows change over time from the Earth warming up and the CO2 rising. But this is the radiation going to space from the Earth to balance what comes in to keep us at a happy temperature. And this is what CO2 keeps from going out. And if there were more CO2, it could keep more going out. And so, yes, the greenhouse effect is, we don't make this stuff up. It is. And this may be one of the most important points here. We don't believe in global warming. Global warming is physics. It is physics that we have no idea how to get away from. There is no serious controversy on this, and especially there is not an other side. This is the best humanity has come up with. Later, I will tell you some other things that people will say you're being too scary or you're not being scary enough. We can talk about policies, and there's a huge discussion about that, but we are raising CO2, and that is affecting the climate. There's not much to talk about there, okay? Now, I can guarantee you that you will find some scientist, if you look hard enough, who will want to argue about something I'm going to tell you. Scientists love to argue. Okay? We really do. And so it's important to sort of separate at this point the difference between one scientist and science. And for that, this question, who speaks for science, one of the solutions to that came from Abe Lincoln. The House, the Senate, and Lincoln, the same day, passed this bill, and they say we need to get scientific advice. We need to be able to lift the lid on these scientists arguing, pull out what they know that's reliable, slam the lid down, and let them get back to work. And so they found this National Academy of Sciences. And so that is the body that is supposed to provide advice to the U.S. government on matters scientific. Some of their early things, one of the first studies they ever did, right? You remember the Monitor and the Merrimack. There's this big fight between ironclad ships. In a very small number of weeks, apparently every navy in the world was building ironclad ships because one piece of hunk of junk with iron on it was trashing really good ships of the line. And that meant that you were putting giant slabs of metal next to your magnetic compass. How do you find north? And so the Navy goes to the Academy and says, how do we find north? The Academy says, these people and these people and these people are telling you stuff and it doesn't work. But this one does. And we will help you retrofit the ship so that it works. Okay? Wilson says we listen to the Academy. Bush Sr. says we listen to the Academy. Bush Jr. says we listen to the Academy. This is getting people working in the public eye for the public good as volunteers to tell you what is solid, what is speculative, and what is just silly. Okay? And so here it is. It's now the National Academy of Sciences, the National Academy of Engineering, the National Academy of Medicine. And this is part, along with the Royal Society and the IPCC and some others, this is the best we have come up with to speak for science. And let the scientists keep arguing, but to tell you what is out there. The Academy has been consistent for decades in telling you what I'm going to tell you next. Okay. So if you ever need information, for what it's worth, The reports are sometimes a shade on the dry side, but they're trying, and they're authoritative, and they're a really good starting point. So you can go see what the Royal Society and the Academy of Sciences say on climate, and you'll find a lot of what I'm showing you here. Okay. So if you want to come take our class, if you want to watch our TV shows, you want to read the book, we've done this. I can go on, guaranteed, for hours and hours and hours on this. But we are raising CO2. This is warming. The warming is occurring. The warming is occurring despite the fact that over the last 30 years, the sun has dimmed a little bit. It has been blocked by particles. We have cut dark forests and replaced it with more reflective grasslands. Our greenhouse gases have caused more warming than we've seen, actually. The warming has the size and the pattern that we expect from our known influences. This confirms our understanding, and that says if we burn at all, what's coming is a lot bigger than what we've done so far. Okay? Any of this you want to talk about later? Great. I've got it. Chapter and verse, we can do this. But this is the best we've got at this point. Nobody cares, right? Global average surface temperature, big whoopee, right? So what does it mean? We will look a little bit at this one. We talked earlier today about this one. This one is one I work on a lot. So what do you get? You get more heat waves and fewer cold snaps. You get heat stress. You get sea level rise. You maybe fewer hurricanes, but there's more fuel, so the ones that get big get bigger. More floods and more droughts. That may seem strange at first, but anybody grow tomatoes in the yard? Right? All winter, the garden's damp or frozen. In the summer, you get a gully washer, and 2 weeks later, you're watering it. You evaporate faster, it rains faster, you make the world more summer-like, you get more variability, you get more floods and more droughts. And this one is really important. The costs rise faster than the temperature. 1 degree of warming, we're used to variability. Right? But we've already had that. 2 degrees of warming, we're starting to move outside what we're used to, and we're pretty well committed to that. Another degree, and another degree, and another degree. You start getting to the point that you can't borrow a crop from somebody in a warmer place because there isn't a warmer place. All right, so let me show you just a couple of little pieces of a much bigger story. This paper came out in the Proceedings of the National Academy this summer, Climate Change in the Fertile Crescent. And if I zoom in on that and blow it up so you can see it, the key points of this report were drought contributed to the conflict in Syria. Think civil war and ISIS and refugee crisis. Humans made that drought 2 or 3 times more likely. Okay, did we cause the drought? We made it 2 or 3 times more likely, and it happened. This is just one paper. But there's been lots more, including in the IPCC reports, that said we are increasing the risk of drought in this area. The drought happened, food prices go through the roof, people get unhappy in an already very unhappy place, and then bad things happen. Okay? Now this is a projection, without huge amounts of burning, but some burning, of drought late in this century when our students are getting really gray. Green would be less drought. All the reds and yellows and purples are more drought. And if you focus in where human forcing has already seemed to be causing trouble, and you'll notice that's red. More drought where it's already not very nice. Now, this is a fascinating report. You might want to go look at it someday if you'd like. A whole bunch of retired generals and admirals, really serious persons. And they said, you know, climate change did not cause the conflict. But it certainly added environmental stressors. And they have noted this for Syria and the Civil War. They noted the role of drought and heat wave in Russia and China on food prices and the uprisings in North Africa, and others. This is a dashed line. It's not a solid line. But if you make an unhappy place more unhappy, it doesn't help anything. And it's pretty clear that we're doing that. This one came out last week. This is from the World Bank, or the World Bank Group. This is still a paper. It's these people's paper. But what they said is that without appropriate actions on mitigation and adaptation, Climate change could force more than 100 million people into extreme poverty by 2030. That's only 15 years out. That's not end of the century. This one also came out in the last couple of weeks. This was looking, and it's published in a good journal, and this one was looking at what does warming do to the economy? Where is the optimum temperature? And what it found, actually, is Canada and, Siberia probably a little help to their economy. They're on the cold side. But all these reds and pinks are serious damage to the economy from warming. It's not ethics yet, this is economy, but you'll see a whole lot more people in a whole lot more places getting hurt economically. And that leads to this. The redder you are, the more CO2 per person per year you're putting up. So red is changing the climate a lot, blue is not changing the climate much. Red is vulnerable to the changing climate. In a warming world, if you have bulldozers and air conditioners in winter, a little warming doesn't hurt too much. If you don't have bulldozers and make walls against the sea and air conditioners so you can work in the summer and winter so you get rid of the winter, making it hot just doesn't help. And so red is vulnerable, blue is not so vulnerable. And so here's who's changing the climate, and here's who's vulnerable to the changing climate. And if those don't look the same, and you believe in the golden rule, there's an issue here. And this is an issue that people are noticing. People like Pope Francis, who said, he commented on this, and he says that this is not a problem that we can leave to future generations. Just in case you're worried about us as opposed to other people, blue would be less drought as we run into the future, and everything in brown is more drought. Okay. And then back to this, the costs rise faster than the temperature does. Like I say, now a degree of warming is a degree Celsius globally averaged. That's 1.8 in Fahrenheit world, but the land warms more than the ocean, and most of us live on land, so it's 2 something or 3 Fahrenheit. When I write 1, think 2 plus, right? And the first degree of warming was just, we've had it, but it's linked a little bit in Syria and a few other places, but so far it hasn't really trashed us. But we've already used it. The second degree starts moving you out of what you're used to, and we're pretty well committed to that. And we're talking about 3, 4, and 5 when you start really moving out of what you're used to, and the cost can go up really fast. Worst case, it gets hot enough that you go outside and you die after a few hours because you just can't lose heat. Okay. So there are uncertainties in this. It's real science, and that's really not good. Because it may be a little better than I said, and it may be a little worse, but it's really hard to see how it's a lot better, and it's really easy to see how it's a lot worse. Because of this basic thing that if you wanted to turn the planet into the Garden of Eden, you're trying to build something that takes getting a lot of things right. It's very, very unlikely that just cranking up CO2 gets everything right. But if you want to break something, like my cell phone or this building, you can do it with a big hammer. And 40,000 pounds of CO2 per person per year that's radiatively active is a hammer. And so the chance that we dump an ice sheet, we go over a tipping point, we wipe out the Brazilian rainforest, we make it too hot to live in parts of the tropics, is out there. And that's not generally in our assessments at this point, because we don't think it's highly likely yet, but it's out there. And so the uncertainties are sort of on the bad side of this. Now, I hope I've scared you. Because it's real. This is the best science, and the scientists who have worked on this that I've talked to say, look, this worries me. This is a real issue. But they also say we can use this knowledge the same way we have used knowledge to defeat problems in the past. If we had more time, if we go through if you take the 3,000 pages of the IPCC report and turn it down into sort of bullets, it turns into something like this. If we use the knowledge wisely, together with what we care about and where we want to go, not only do we get a cleaner environment, but we get a bigger economy. We get more jobs, we get greater national security, and we honor the golden rule. You don't always hear this, that ignoring this has economic costs as well as environmental ones. And that's really the conclusion of the whole scholarship on this. And then you come to this one, can we do it? Can we make the economy better by building a sustainable energy system? I'm going to give you the tiniest little window on this, and then if you want to ask about it later, we'll go into more of it, okay? But the answer is yes. So let me show you this. 2,000 calories per person per day, where do we get it? Croplands are in red up here, or orange. The oranger it is, the more of the area is used for crop. Grazing lands, we can't eat it, but a cow or a sheep or a goat can, and then we can eat them or something they produce. And so the land that gives us our 2,000 calories per person per day is what's colored up there. Now suppose that we decided to use modern, shovel-ready, existing technology to make more energy than is used by all of humanity. Just for reference, I'm going to show it to you by putting a solar farm in the Sahara. No one's actually going to put the solar farm in the Sahara, but suppose that we said we're going to make more energy with existing shovel-ready technology than is used by all of humanity today. How much would it take? It's that. Okay? Everything in color is where our 2,000 calories come from, but powering humanity with more than we now use with a modern solar farm, that much area. Now, don't kid anyone. That's a lot of solar cells. Could we do that in a year? No. Could we do it in 30 years? Probably yes. And we're getting better all the time. Now, this one's fun. Before Lincoln is president, before Lincoln is signing the National Academy of Sciences into existence, he's out on the stump, and he has a speech about learning and knowledge and science and engineering and patents and inventions. And in part of this, right, Discoveries and Inventions, a lecture by Abraham Lincoln delivered in 1860. And as part of this, he looks at Illinois, and he says, wow, you people could use power. He says, the wind is an untamed and unharnessed force, and one of the greatest discoveries to be made will be the taming and harnessing of it. Okay? This is our bedrock. This is what we are. This is what we do. If we put a wind farm on the windy parts of the plains and deserts of the world, that's sort of 5 times human energy use right now. Doesn't have to be in the cities, doesn't have to be in the forest, doesn't have to be in the water or the ice. Just the windy parts of the plains and deserts, more energy than we use by far, right? And so this is from our TV shows, and you put 5% of the ranch into these things, and they get 5 to 10K a piece each year. They call it mailbox money because you go out to the mailbox and you get money, and the rest of the ranch is in these things, and they actually don't, that's not worth 10K, okay? That is per year. And so it's sort of amazing. Ranchers who couldn't possibly care less about climate change love wind energy. And in case you missed it, as of day before yesterday, this was in the newspapers, that there actually is one company in Texas that is trying to smooth out demand for their electricity a little bit by giving it away at night. It's free. You turn on, you charge your car, you run your laundry, whatever, it's free. Because there's so much wind on the grid that it just doesn't cost much. So, we learned to farm to get over starving to death. And we aren't hunter-gatherers for food. And if we all went out and shot a deer to try to feed ourselves all winter, the deer wouldn't make it through winter. You know, we have to farm to do this, but we're still hunter-gatherers of energy. And you've seen a little of the history of our ancestors walking through problems. In the 1600s, in the town of Eastham on Cape Cod, when the Pilgrims got to Cape Cod, it was goodly wooded to the shore. By the late 1600s, there were no trees left. the ravages of deforestation and the loss of fuel were so bad that Eastham outlawed your own ability to cut your own tree on your own property. When the scarcity hit, the government got in your face. We've hit this over and over and over again, and we are the first generation that can look at each other in the eye, square and honestly, and say, we know how to fix this. We know how to build a sustainable energy system that'll power everybody on the planet, essentially forever, in a way that will help the economy, as well as the environment, as well as the ethics and the golden rule. Is it a huge task? Of course it is. Is it a possible task? Of course it is. And so you sit there and you look at this, and so I will leave you with a picture I took in Greenland a few years ago. Can we have a world with icebergs and rainbows? And the answer is unequivocal, yes. Thank you. And I am very happy to take questions. I think that we're right down front to start with. I think the acoustics are good, and if you're not really loud, I'll repeat it. So,
what about politics?
What about politics? Yeah, this is difficult at this point. We're missing the debate tonight, I think. So, but at any rate, thank goodness. Yes, it's the first time I testified to a subcommittee of the U.S. Senate was a dozen years ago. And it was chaired by a Republican who wanted to put a price on carbon to keep the government from passing lots and lots of little regulations. Just get a price on and get out of the way. This Republican wanted us as scientists to scare the pants off of people. And I think this Republican was unhappy with us because we were so measured in our tone as opposed to being scary. And so a dozen years ago, doing something about this in a conservative way, a market-friendly way, was considered mainstream for one of our political parties, and the other one might have looked more to government action rules and regulations. That day, if you had told anyone in that room that we would ever live to see two gay people get married in America, we would have laughed at you, because it was so inconceivably ludicrous that we would ever do that. And so what was absolute political mainstream and what was politically impossible have completely switched in barely over a decade. And what that means to me is that it's possible for these things to switch back. I've had the remarkable experience of being in a private meeting with some scientists and some senators when I'm not going to tell you who was there or what we said. My impression was that they are among the most frustrated human beings on the planet because they were elected to do things, and right now something bigger than them has happened and they don't know how to do it. And that they would be very grateful if we would give them the environment in which they could go back to doing their jobs. So I think this can happen. I have no clue how to make it happen. I go out and give a lot of talks, but I'm not sure if that's doing it or not. But right now it looks a little bleak sometimes. There was a report recently from a scholarly paper that the United States is the only country, the only major democracy in the world with a major party that basically rejects the science on this. And so we get a warped view because most other places don't have this same view that we do. And this is a recent thing, and I don't think it's actually part of the DNA of this particular party.
Thank you.
Other questions? That was sort of a heavy one to start with. Come on. Yes, okay, over here, then, yeah.
Scientists try to be collegial with some of the major companies in the world, energy companies in the world, to try to convince us, surely scientists within those companies know better. But the companies with the direction they're going, they know it's immoral, it's unsustainable. Are there any groups trying to bridge that gap to bring about a major, you get a major company like Shell doing something, not the stuff we talked about this morning. So. carbon.
Right. So the question was, are scientists working with the major companies to try to bring them along? I think it's fair to say yes. I think it's fair to say that there is room for improvement. I would plead that we're spread thinly, but I think there are real efforts, and I have phoned in talks and gone to talk at a couple of oil company events, actually. And the science, and you've probably seen the news recently, that it's very clear that the scientists working for some of the major oil companies told them a lot of decades ago that this was real. So, and you're seeing more and more, starting from the reinsurance industry, but you're seeing more and more companies that are actually saying, we need to do something about this, both because it's a big issue and because policy guidance moving in a predictable way is useful. And the idea that maybe we wait until there's a crisis and then we have to make an extreme change, they hate that. And so giving long-term guidance, I think that you'll find that many of the big companies now are thinking in that direction. And so you'll see there's, 100 companies that said we want something done in Paris. I think that one of the, I don't remember the details, but there are some of these things bubbling along. So a lot of people get it. The ultimate big picture thing, that pretending this doesn't exist leads to more crises. It leads to damages that actually make business harder, is important. There is profit to be made here. The IPCC, those 3,000 pages of the IPCC, one of the things that drops out the end is what we call the social cost of carbon. And the social cost of carbon is the damage that emitting the CO2 to the air does to society. And it's a dollar number. And there's a lot of uncertainty in it, but I think all of the studies now show that it is a real number which is much bigger than zero. And so when you buy fossil fuel, the price you pay is for the goods you get from the energy from it. And the price reflects the good we get, but the price doesn't reflect the bad we get. And if you buy a solar cell, the price includes the fact that the solar manufacturer may have to pay the landfill to take the scrap, and they have to pay to get rid of it. And if you go to the restaurant and have dinner, the price includes the fact that they have to pay a trash hauler to take the trash away, and they're paying a sewer bill when you go to the bathroom. But when you buy gasoline, you harm society with the CO2. You pay for the good, but you don't pay for the bad. And we call that the social cost of carbon. But if we called it the profit that could be made from wise things that would make society hum better, which make the economy bigger, which means more money flows, maybe it would come out differently. And it is, you can think of it as a subsidy for fossil fuels over other things. You can also think of it as profit that is waiting to be made, because by not damaging the society, you make the economy bigger. So there was a question back here, and then one down for, yeah, okay.
So
When
when do you predict the end of fossil fuel use?
do I predict the end of fossil fuel use? I wish I knew. You can think of a future in which, right now, right, so 5-6 years ago, when I started writing the book that turned into our PBS miniseries, I could not, with a straight face, say that solar was really competitive with much of anything. And right now, it is very clear that big utilities are tying themselves in knots trying to figure out what to do with solar, because it has gotten cheap enough that it is affecting their business model. And you have some companies that seem to be trying very hard to block wind because they can't compete with it, and other companies that are giving it away for free at night. And so the fact that right now, renewables have gotten to the point that they are sufficiently competitive that real businesses with real bottom lines are having real issues with what to do about them, and some of them are trying to find ways to hold down the renewables so they don't have to compete. That could make things really optimistic. On the other hand, 50 years is not long for the life of a big plant. And so the question of whether we will take the actions that make the price of the fossil fuels reflect their full cost or not, I believe has a huge amount to do with how rapidly we move to a sustainable energy system. Across the board, when I am not an economist, I am a geologist who does ice sheets, but when I have spoken to economists, they really love the idea of putting a price on carbon, and they really like a gas tax, a CO2 tax. And they do something that's sort of like this. So if you will, I don't know if we're having anything alcoholic or not, but we tax alcohol, and we do so to raise money for the government and to reduce drinking. And we tax tobacco, and we do that to raise money for the government and to reduce smoking. And we tax your paycheck, and we do that to raise money for the government. Any economics students? And reduce working. And any good economist will say, look, if I say I really need some help, I'll give you $10. Can you help me? She might. And if I really need some help, I'll give you $5 and I'll give the government $5. You're less likely to. By making work less valuable to people, the tax on your paycheck tends to make them do other things. And so the economists have said, what would happen if we taxed carbon and we used that to reduce the tax on your paycheck? And the broad answer is, if everything else I set up here is an evil lie, it does not hurt the economy. Replacing fossil fuels is a huge deal, and that will distort the economy. But replacing willing, bright workers is also a huge deal. Because what I told you is not an evil lie, in fact, the economy ends up bigger if you do something like this than if you ignore it. And so across the board, the economists just love this idea, putting a tax on carbon and using that to reduce some other tax that we don't like. And then they say, suppose that somebody else decides they don't want to. We tax our carbon. China has said they're going to get a market going. Europe has one going. So suppose we, Europe and China, get together and say, we will tax our carbon and we'll use the money to reduce other taxes we don't like. Some other country says, we don't want to do that. We say, fine, you don't have to. But China, the US, and Europe will put a tariff on everything that goes into and out of your country with us, and we'll keep the money. And you'd have to tweak international law to do this. But suppose that half of the world economy said to the other half, you can tax your carbon and keep the money, or we'll tax your carbon and we'll keep the money. What would happen? And so there are, and I'm not saying this is the right policy. Carbon tax is regressive. It hurts poor people more than wealthy people. There are other issues. There will be regional impacts. There are some states will hurt more than others. So I'm not saying this is the right policy. But I'm saying there are policies out there that serious people have looked at that say they will help the economy and that they can be implemented. And they're not that complicated. And if you're a real libertarian and you hate the government getting in your way, putting a little more price on coal, oil, and gas where they come out of the ground or into the country and spending less time snooping into your personal finances is not necessarily a huge amount of government intervention. In fact, it probably means less government. Yes?
What do you think an achievable mix of alternative energy sources would look like to make this work?
Right, so what would an achievable mix of alternative energy sources look like to make this work? And almost certainly it's evolving. So in the short term, you put a price on carbon, and in the short term, almost all the studies say that we will use less. And conservation becomes very big in a hurry. Right now, most of the conservation actions pay for themselves, and this would make them pay for themselves even more, so this is just free. Then what happens long term, if we took 1/100th of 1% of the sun's energy reaching the top of the atmosphere, that's more energy than humanity uses. So sun is huge. Just little bits of it are more than we use. 1% of the sun goes into wind. And so wind is actually much bigger than we need, but it's not as big as the sun is. 1% of the wind goes into currents and waves, and that's actually not big enough to run everything. So if you're on the coast, you probably are going to use some currents and waves. And if you have to build a breakwater and you want to slow down the waves that are coming at your city on the rising sea, you could just build a wall, or you could build a wall with a power generator in it. And so you almost guarantee that there will be people using waves and currents, but it's pretty clear that won't be the big piece. Hydroelectric, there isn't enough to run humanity, and my personal belief is that at the point where there's enough hungry people, we will release the water on the time scale of growing food, not on the time scale of making power. So right now, be honest, right? So the tomato farmers, right? Across Pennsylvania, there is almost no irrigation. But all of us who grow tomatoes in the backyard water during the summer because we grow more food. If there's enough hungry people, Pennsylvania will irrigate. And in some real sense, a river that reaches the ocean is food that was not grown on the way. And so my gut feeling is long-term hydroelectric is not a big piece of the story. My guess is it's mostly wind and sun. Batteries may turn out to be your car. So if you have a sufficiently smart electric grid and you have a car that has batteries on it and you plug it in when you park, if the grid has extra power, it gives it to you. And if there's a little fluctuation and they need a little back, they buy it back. And if some of them, if the universities had plug-in hybrids, so there's a little biodiesel on board, that would do it. That'd be the storage that would stabilize the grid. There may be other pieces of storage that go into it, but my suspicion is that in the time that you run through a new set of cars, there's an immense amount of storage out there, and you just need to be smart about using it. So long term, if you talk to the people who've put serious plans forward, and there's a couple dozen of them, they tend to be fairly heavy on wind and sun, and the long term, it's dominated by that. There's very good interest in hot, dry rock for geothermal. That could be done. It's not yet at the sort of shovel-ready stage. There is a long and fascinating discussion about nuclear. There are people that if you say nuclear, they get up and leave. And there are people, if you say no nuclear, they get up and leave. That is the topic I have found that is most likely to find informed, interested people trying to move forward who bitterly disagree. And my immediate response is that has to change before it can be much of the answer. We spent a lot of money on nuclear research without changing the technology from 50 years ago because we haven't been working on the technology. And I have this nagging suspicion that it's less shovel-ready than we think, because we haven't been building for a very long time, and that sort of engineering know-how that real engineers get when they need to do real things is dying, because we haven't built any for 50 years. And so ultimately, I suspect it's wind and sun, but I also suspect that it is very strongly customized for who you are and where you live. Yeah?
I'm an economist.
Yes.
I have a question about ice sheets. So when I first, as an economist 20-some years ago, paid attention to climate change, physical scientists were telling me ice sheets are pretty stable. Projections of sea level rise from lost ice sheets, very far off in the future. Seems like over time, what physical scientists have learned is, maybe it's more complicated than they thought 20-some years ago. What's the state of the science on ice sheets? Should we be as afraid as I think we should be, and what you've been learning in the last few years?
Yeah, they worry me a lot now. So this is my specialty. I do some of the work on this. I wrote a master's thesis. Before my PhD, I wrote a master's on the 10,000-year timescales. It's out there, Ali and Williams, 84. And then we're working in West Antarctica, and my colleague, Sridhar Nandakrishnan, puts out seismometers, and he listens to little earthquakes under the ice, and he realizes that when the tide goes down, 100 kilometers away, the ice in here lurches forward and it makes earthquakes under it. And he and I modeled this, and then he went down and he put GPS receivers on it, and it works. The tide goes down, and 8 hours later, the ice up here goes faster. And we said, oh, crap. And then we started seeing this happen in various places as the warm waters have attacked the ice shelves, and that 8-hour time scale's about right. It happens. And so then we're sitting here, okay. And then we say, oh, maybe we're okay. Most of the ice is going to go faster. It's going to raise sea level, but it all sits in these narrow troughs. And so it can go faster, but it can't go really, really fast. And then we said, oh, my goodness, Thwaites Glacier. And I talked about this earlier today, actually. But in the worst case that we can imagine, right? You remember Hurricane Sandy? Hurricane Sandy brought a few feet of extra water to a little piece of one coast for a few hours. Right? I'm downplaying it, but really, it wasn't the whole coast of the U.S. It sort of hit the New York area. And the absolute peak of the water was really only a few hours. It starts down with the tide. And while the peak above the mean high water was 13 feet, most of it was under 10, 5, 7, 8, and that got in the subways. And West Antarctica potentially, once it gets going fast, in a human lifetime or less, could give more water than that to all the coasts of the world essentially forever. Okay? Right now, that's in my tale of bad things as opposed to in my most likely. But if you want the black swan, the impossible collapse that happens sometimes, that's it. And you plan for a meter, maybe 2/3 of a meter, maybe 4. And that we would love to do better with that. It is frustrating beyond any belief. But it's the rate at which the ice sheets have been shrinking, averaged over the last 20 years, is that much sea level a year. And at that rate, they would take 100,000 years to go away completely. The equivalent, 100,000 years to go away completely, is me going on a diet for a year and losing 1/3 of a potato chip. Okay? The uncertainties of what an ice sheet could do, they can't go a lot slower than that. They can go faster. Yes? And then.
Anticipating politicians being politicians and political rhetoric, do you think global climate accords and global science accords are things that are actually going to bring about change, or is it going to be coming from the global economies just having to deal with this?
So if you didn't hear, whether I think global climate courts, global courts are going to bring about change or whether it's the economy, my suspicion is it's the economy. It's proven fairly difficult to get the U.S. to get really, really excited about giving any level of power and sovereignty to some courts. So I suspect in the short term it's the economy. Yeah.
Well, there seems to be a really clear disparity between developed countries and developing countries when it comes to the impacts of climate change. So how do you think that we can address that issue?
Right. So the question was, there's this huge disparity between developed and developing countries. How do we address this? I wish I knew. And I'm sorry, and you may have more insight than I do, to be perfectly honest. There are commitments being made, helping in some way is there. My suspicion, from the biggest picture thing, our fossil fuel companies are fantastically efficient. And they have worked really, 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 really hard to drive down the price. And the idea that somehow we're going to drive it down so far that all of those poor people can live like we do on fossil fuels, I personally think this is very, very unlikely. I think that, at the halfway point of whale oil, what did the price do? It went way up, not way down. And this is a bank account of fossil fuels that's not growing. So at some point we run out. You know the story. When I was a kid, these many decades ago, if you wanted to talk on the phone, you had to go over here and stand next to the wall, and there was a copper wire that went from there to the rest of the world. And Africa's never going to do that. Right? They skipped over something. And that was, there's a lot of big holes in the ground that copper came out of. And there were a lot of cables strung in a lot of places and a lot of people standing next to walls that is jumped over by smart. And so my suspicion is that because the renewable energy is becoming so competitive, that if we really wanted to help, one way to do that is to start thinking, how do we help them make this transition directly to something sustainable rather than going through giant coal plants?
Maybe one more question. And then
Any?
we have-
Yes, one more, and then, yeah.
I was just gonna ask if you're seeing more of a global collaboration with
Are we seeing more of a global collaboration with everything? I think that the photovoltaic, the practical solar cell is invented at Bell Labs, but if you buy one right now, it won't come from Bell Labs probably, and it might come from a whole lot of places, including China. The science is very, very international, and we're watching in fascination as the international community tries to make it work in Paris on going forward. We chatted about this early, so if you heard this, I'm sorry for repeating myself, but the photovoltaic cell dates from the earlier 1800s originally. The practical one dates from the 1950s at Bell Labs. As of 2009, I don't believe they were very competitive with anything. As of 2015, I believe they're very competitive with a lot of things. The time from when we got started on turning solar energy into electricity to the time it was actually a commercially competitive product was well over a century. I personally will be very surprised if the negotiations in Paris over the next weeks actually produce the final solution that will get us where the world wants to go. I suspect they are doing something that is harder than getting silicon to spit out electrons when it's hit by photons. I am optimistic that they will make progress, but if they don't make enough progress to actually solve the problem, I think that is predictable and not deplorable. So for what it's worth, I don't think it's easy to get everyone to sit down, shake hands, and make up. And so I think what we want to do is look at the slope and not the final point. That's an opinion, but so.